The fact that a pi bond has its electron density above and below the interatomic axis introduces us to the concept of stereochemistry in the context of alkenes. Okay, so stereochemistry is defined as the study of how molecules are arranged in 3 dimensions. So for an alkane, such as butane, there is free rotation about any one of the carbon-carbon single bonds. Okay, what's most interesting is the central carbon-2, carbon-3 bond, and we will consider the ramifications of the fact that such free rotation exists in the next unit. But suffice it to say to start with that if you have a molecule, a conformation, where one CH3 is going away from you and the other CH3 is going towards you, and another drawing in which both CH3s are going towards you, these are just 2 representations of the same molecule. They are not, in fact, 2 separate molecules as a result of this free rotation. And incidentally, I'm going to have to make extensive use of molecular models when talking about stereochemistry and 3-dimensional structures. Any good model kit tries to represent reality. In other words, if a model allows you to do something, it is fairly easy for that phenomenon to happen. Since the model kit allows me to easily rotate about a carbon-carbon single bond, rotation about that in the molecule is fairly easy. However, for alkenes, it is impossible to rotate about a carbon-carbon double bond. Can't do it without breaking the pi bond. And that should be fairly evident from this picture here. Remember, I have said when we've talked about pi bonding that you can overlap red with red and blue with blue, but you cannot overlap red with blue. In order to do this rotation, you would have to move those reds that are overlapping with each other and those blues that are overlapping with each other, move them apart. Initially, you would move them perpendicular to each other, or if you tried to go further, you would end up overlapping red with blue. Doing that entails breaking the pi bond. And a molecule is not going to break a bond very lightly. It will sometimes break a bond during a chemical reaction, but when a reaction is happening, there is usually a serious energetic gain at the end of the reaction that will allow it to pay an energetic price to break a bond to start with. A molecule simply spinning around in solution does not have enough energy to break any bonds. If it did, it would not be a stable molecule. Okay, so for all intents and purposes, it is impossible to rotate about a CC double bond. What that means is that the following 2 structures, okay, A on the left here, B on the right, the following 2 structures are isomers, even if they have the same atomic connectivity. Okay, so these are structures in which you have 2 carbon atoms and 2 chlorine atoms. In this case, the 2 chlorine atoms are both on the same side of the carbon-carbon double bond in structure A. In structure B, the 2 chlorine atoms are on opposite sides of the carbon-carbon double bond. One is on top and one is on the bottom. Okay, so these molecules are isomers, but they are what we call stereoisomers, and they are not constitutional isomers or structural isomers. So the definition of stereoisomers is that they have the same atomic connectivity. Okay, in both of these structures, you have chlorine, carbon, carbon, chlorine, chlorine, carbon, carbon, chlorine. The connectivity is the same, but you have a different orientation of the atoms in 3-dimensional space, whether they're on the chlorines are on the same side or the chlorines are on opposite sides. Okay, even more specifically, and this will become more obvious in Unit 2, these molecules are what are called diastereomers. Diastereomers are simply the term we use for stereoisomers that are not mirror images of each other. We will get to mirror images in Unit 2 in a later lesson, but it should be fairly obvious to see that these two structures are not mirror images of each other. Okay, so this begs the question, how do we tell the difference between these two structures if we're trying to name them? Remember the principle from our lessons on nomenclature that every unique structure has to have a unique name. But based on the rules you know so far, both of these structures would simply be called 1,2-dichloroethene. What do we do? Well, for structure A, in which the two chlorines are on the same side of the double bond, we add the word cis to the front of the name. Okay, in fact, it doesn't have to be chlorines as long as the two non-hydrogen atoms are on the same side of the double bond, it's cis. For structure B, when the chlorines are on opposite sides, we add the word trans. Therefore, structure A would be called cis 1,2-dichloroethane. Note that the word cis is in italics and it is separated from the rest of the name by a dash. And then structure B would be trans 1,2-dichloroethene, also in italics and separated from the rest of the name by a dash. Okay, so cis and trans are necessary whenever both alkene carbons have two different groups bound to them. Okay, so this carbon on your right has a chlorine and a hydrogen, two different groups, and the carbon on your left also has a chlorine and a hydrogen, two different groups. When you have that situation, then cis and trans are necessary, even if all of the atoms are carbon atoms. All of the non-hydrogen atoms are carbon atoms. So we can consider 2-butene, okay, molecule that contains 4 carbons with a double bond between carbon 2 and carbon 3. You can think of the 2 carbons as both being down in the left-hand structure. In other words, on the same side of the double bond. That will be the cis isomer. And then in the right-hand structure, where one carbon is down and one carbon is up with respect to the double bond, that is the trans structure. So you need cis and trans for 2-butene because each of those alkene carbons have a hydrogen and a CH3, two different groups bound to them. However, for 1-butene, in which the double bond is between carbon 1 and carbon 2, you don't need cis and trans. Cis and trans are not used because the terminal carbon, carbon 1, is bound to 2 hydrogens. It has 2 of the same atom bound to it, so therefore it does not meet the case in which you need cis and trans. You need cis and trans when both alkene carbons have 2 different groups bound.